All right, Unit 4 is all about how derivatives and second derivatives can help us understand what an original function is doing. Okay, so that's Unit 4. Okay. What do I mean by helping us understand? Well, derivatives and second derivatives, if I understand the signs of derivatives and second derivatives, I will be able to, without knowing what the original function looks like, understand how this is going to be shaped this way and then shaped this way, and how there'll be like a little bit of a maximum here and then a minimum here. And we will be able to sketch an original function just by knowing what the signs of its derivative and second derivatives are. Okay? Now, the first thing we will talk about, and the first kind of part of this overarching unit, is critical points of a function. Okay? A critical point of a function is when its derivative equals 0 or is undefined. Sometimes it's called a critical number. So if I said, what is the critical point of f? It'll be when f prime equals 0 or is undefined. Today, all we will be doing is finding the locations of critical points for functions. That's it. Which means all we're going to be doing is taking derivatives, setting them equal to 0, and solving. Okay? But why? What's so special about these critical points? Well, let's look at this sketch of a function. Okay? And let's pick out all the locations where we have a derivative equal to 0 or a derivative that's undefined. We have here, 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 the derivative equals 0. Derivative equals 0 here, here, and here as well. Here we have a sharp point. That's when my derivative is undefined. Okay? What is going on at those locations? Well, we have what we call extrema. Extrema are extreme values of a function. What are extreme values of a function? We'll call them local maxes or mins. We'll call them maxes or mins, really. Okay? There are two types of extrema. We have local or relative extrema, which are going to be our local maxes and mins. And we will have absolute extrema, which will be our overall maxes and mins. Okay? In this unit, we will stick to local or relative extrema. We will look at absolute extrema at a later date. Okay? Well, if I look back on my graph, where we have derivatives equal to 0 or being undefined, we have these local maxes, local mins. Okay, we won't care about designating any of these as absolutes. Like probably this one we could see is probably, maybe it's the same value as this. We could have two absolute maxes. But for right now, all I know is that this is a local max. If I just look at a specific part of my function, you would say that is the max of this kind of localized section, right? Same with this guy here. This is a local min. It's not the absolute min. There are smaller values for my function to the right and to the left. But if I look at a localized section, that will be the minimum value of that section. Okay, this is a local max as well. Here, when my derivative is undefined, I have a min. And here is another max. So why do we care about critical points? Because critical points are where maxes and mins occur. I'm going to leave a space after maxes and mins and before occur. If you didn't leave a space, you'll be able to draw in an arrow. Don't worry about it. Now, I left the space there. For what reason? If we go back to this section into this graph, you should be like, hold on, Mr. Messner, wait a second. You made a mistake. We're missing something. Can anybody figure that out? Mr. Stockton? Yeah, the graph right here at the beginning, right here, looks like we have a horizontal tangent, right? The derivative is equal to 0. Similar to like x cubed. If I look at x cubed, you know, it looks like this. Well, I know the tangent slope at 0 is 0. However, this location is neither a max nor a min. This is kind of a flat part that, you know, comes up and then keeps going up. So let's go back up here and change this. We'll say where local maxes and mins could occur. Because there will be something that is consistent. Every max or min will occur at a critical point. However, not every critical point will give us a max min. I'll say every extrema will occur at a critical point. But not every critical point will give us a max or a min. Okay? For today, all we will be doing is finding critical point locations. Okay? That's it. Just finding the critical points. Next class, we will examine whether the critical point will be a max, a min, or neither a max nor a min. Okay? So it's actually kind of simple today. Today, we're just going to be taking derivatives, setting them equal to 0, or seeing when they're undefined, and solving. Next class, it gets, you know, a little bit more complicated because we'll have an extra step after we find these critical points. Okay? But we just want to first practice finding critical numbers or critical points for functions. So I have 1, 2, 3 functions. These are just simple polynomial functions. Most of the functions we'll be dealing with are just like this. Not super complicated, just polynomials. And we know polynomials like x squareds or x cubes sometimes could have, you know, a couple max mins, like x to the 4th. We will try to find the locations of these, you know, humps. To find the locations of the humps, we'll be able to take the derivative, set it equal to 0, to find the possible locations of the humps. To find the critical numbers, just take your derivative, set it equal to 0, or see when it's undefined. Let's start with this first one on the left, 3x to the fourth minus 4x cubed. I will take the derivative. I will set it equal to 0 or see when it's undefined. It's important not to forget about the undefined part. For a lot of these, we will find that it won't matter. Like for this one, this doesn't matter. Why not? There's no denominator, right? We're going to be undefined when our denominator equals 0. In this situation, no denominator. It'll never be undefined. So we can ignore this. So we just need to figure out for which x values this equals 0. Well, again, we have something equal to 0. We factor to get products. We set those individual products equal to 0 to help us solve. So I have 12x squared that I can factor out of both of these terms, giving me x minus 1. Now, this is a term, this is a term. When will these individual terms equal 0? Well, when this is 0, the entire thing will be 0. When this is 1, the entire thing will be 0. Okay? After we find that, we think to ourselves, hey, those are possible locations of maxes and mins for that original function. I don't know what they are right now, but that's all I'm thinking. They are possible max-min locations. Okay? You guys do the second one. Check your answers with a neighbor.
We've already done this at physics C.
Okay, so very important to understand, because some of you have made this mistake before. And just because you have a 3 outside does not mean we have 0 as a possible answer. Okay, if this was 3x, then this term would be 0 when x is 0. This term would be 0 when x is 4. This term would be 0 when x is -2. But we don't have that x, so we just have 2 possible solutions, 4 and -2. That is it. Okay? If I plugged in 0, I'd get 3 times -4 times 2. That doesn't work. Okay, do the last one as well, if you haven't done so already. Again, those are possible locations of maxes and mins. We have x to the fourth plus 4x cubed plus 4x squared. Let's make sure we do that one as well. Check your answers with the neighbor again. All right. We're all pros here. Good. We should get 3 answers, 0, -2, and -1. We have 0 in this answer because we have this 4x on the outside, okay? We factor first, then we factor to solve that trinomial. Okay, they're not always going to be that easy. So here, we're going to have some derivatives with denominators. And we'll have multiple terms. We'll see how we'll deal with this, okay? Now, I have g of t. This is just to have us comfortable with different variables, different functions, instead of just using f. Typically, we will be talking about f in this unit. But if we're asking for the critical points of g, just find when g prime equals 0 or is undefined. Now, the second half, the whole undefined piece, this will come into play. Now, I want you guys to find the derivative of g first. And let's see if we get the correct derivative of g. If we have started by noticing this is a product and we should use the product rule, good. If we then notice that this is a chain and we need to use the chain rule for this one, good. Okay, stop after you get your derivative. Make sure we are here. This is what I got. And you can rewrite this if you wanted to. I will rewrite it like this. Okay, that's my derivative. Okay, the derivative of the root 4 minus t is 1/2 4 minus t to the -1/2 times -1, but then don't forget to multiply by the t, which is your first one, f prime g plus g prime f. Okay, well, I'm going to set this equal to 0 or c when it's undefined. Whenever we have multiple terms, one with a fraction, since I have both this and this, we know we're undefined when we have a denominator equal to 0. Well, if I just had one denominator, I could set that equal to 0. That's easy. If I had a numerator, and a denominator. Numerator I can set equal to 0. Denominator I can set equal to 0. That's good. If I have two terms separated like this, it's not as easy as that. So I'm going to combine these two terms by using a common denominator. Which means this term over here on the left, I will multiply the top and bottom by the denominator over here on the right. Giving me 2 times 4 minus t plus negative t, now all in one piece of a fraction, divided by my common denominator, 2 root 4 minus t. Now this is going to be easier to tackle now that I have one numerator and one denominator. I know when my numerator equals 0, that'll cover this part. If my denominator equals 0, that covers this part. So I'm just going to take both the top and the bottom and set them equal to 0. And I will find when my fraction will equal 0 or when my fraction is undefined, which will be when my derivative equals 0 when my derivative is undefined. Okay, so I have first f prime equals 0. That's the top. Again, this is g prime. So g prime equals 0. That's the top. I have 8 minus 2t minus t equals 0. I will solve that. Subtract 8 divided by negative 3. And then I will see when g prime is undefined. That's when the denominator equals 0. Now, you can divide both sides by 2. 0 divided by 2 will get rid of the 2, but not change the right side. You can square both sides. When I square both sides, I get rid of that square root. And then I can solve for t. And it just ends up getting rid of one thing at a time, getting me t is equal to 4. Okay, and I could have just kind of figured that out in the first step if I wanted to. Okay. Now, I have found my critical points, my possible locations of maxes and mins. Okay, it's kind of involved, but that's what you got to do sometimes. Let's tackle another one just like this for practice. Ooh, what's that one? Let's go ahead and do this guy over here on the right. X root 3x squared minus 12. You get 4 answers, plus or minus one number and plus or minus another number. How do we do? We checking our answers? Do we get it? We should get plus or minus 2 and plus or minus root 2, I believe. No? Yeah? Yeah? All right, let's see. Okay, remember you have to multiply by the derivative of the inside. The derivative of 3x squared minus 12 is 6x. Well, don't forget to multiply by the first one. So that gives me root 3x squared minus 12 plus 6 divided by 2 becomes 3. X times x is x squared over root 3x squared minus 12. We'll set this equal to 0 or c when it's undefined. I will give this a common denominator. It's really the same as the other problem. Multiply the top and bottom by root 3x squared minus 12, giving me 3x squared minus 12 plus 3x squared divided by root 3x squared minus 12. See when that's 0 or when it's undefined. Set the top and the bottom equal to 0. Okay, the top will be when it's equal to 0, the derivative. I get 6x squared minus 12 is equal to 0. X squared is equal to 2. X equals plus or minus root 2. Here, when the derivative is undefined, is when the bottom equals 0. I have 3x squared minus 12 equals 0. You end up with x squared is equal to 4, or x equals plus or minus 2. Okay, good. Now, hold on a second. If I go into the original problem, in the original function, we should probably check our critical points. I should probably done it on here because I have square root of 4 minus t. If I had a value like 5 here and had the square root of 4 minus 5, it would be the square root of negative 1. That would be outside of our domain. That would be imaginary. Fortunately, 8/3 is less than 4, so that's fine. That works out. If I plugged in root 2 or negative root 2 into my original, I'd have 3 times 2, which is 6. 6 minus 12, which is negative 6. That'd be the square root of negative 6. Now, actually, that's outside our domain. If we looked at these values, actually, on the imaginary portion of the graph, you'd see that this would be interesting locations. However, for this class, we will be sticking with the real portions of graphs. So we will be saying that these are not critical points, and we will just not worry about them because they're not in our domain. So after we find our critical points, make sure they work in our original function. We'll say this does not work in original. But these do. Okay? Let me give you another one. You might not get a pretty looking answer, but we'll get an answer nonetheless. Go ahead and tackle this guy. All we have to do is take the derivative, set it equal to 0. Or see when it's undefined. Pause here if you got here. Sometimes you guys are freaked out by fractional powers. Don't be freaked out by fractional powers, okay? These are fine. Leave them, okay? Because we can work with fractional powers, piece of cake. Now, we have this set equal to 0 or being undefined. We will tackle it just like the other problem. We can give this a common denominator so that we just have one fraction. We'll set the top equal to 0, we'll set the bottom equal to 0. I will multiply the top and the bottom by what was in the bottom, 3x to the 2/3. Now let's see what happens. I get 1 plus 12x to the 2/3 over 3x to the 2/3. Now I can set the top equal to 0 and solve. Now how do I solve this? I will subtract 1, divide by 12, and then take both sides to what power to solve for x? Yes, to the 3/2, right? When we take a power to a power, we multiply the powers. You end up taking both sides to the reciprocal of our original power, because 2/3 times 3/2 just gives me 1. So I have x to the first. Well, that equals -1/2 to the 3/2. Now, I actually cannot find this number. This is an imaginary number. It's -1/2 cubed square rooted. The -1/2 cubed would be -1/8. Can't take the square root of -1/8. What happened? Question? Oh, I don't know. I forgot that one there. Thank you. So I'd have to cube -1/12 and then take the square root of that negative number. I can't do that. So since this is an imaginary number, we would not worry about it. However, I'd expect you to be able to solve something like that. Okay? Really, the other comes from 3x to the 2/3 setting equal to 0. Well, you divide by 3, you take 0 to the 3/2, and you get x equals 0. So you get that one. Okay? We need to be able to do this for sure, because sometimes we will get an actual value. In this case, we can't take the square root of a negative, so we don't have to worry about it. But we need to be able to do this process with these fractional powers, which is why we did this example. Okay, we could have some trig functions. This is just a reminder of having to solve trig functions set equal to 0 when we have something other than just x. Here we have sine of pi t. I don't know why I have f of x. It should be f of t. The variable should be the same. Okay, I'll do this one really quick. Remember, when we're taking the derivative, this is a chain. This is the sign of stuff, and then there's pi t in the middle. The derivative would be cosine of pi t times pi. Derivative of this is cosine. Derivative of this is pi t. Just pi. Okay, we set that equal to 0, or c when it's undefined. Now, what's nice is that I can divide both sides by pi. The pi's just go away. This pi goes away. This pi would stay, right? It's a product, and we can't divide out this pi. It's inside the cosine, the trig function. So I have this. Fortunately, cosine does not have a denominator, so I don't have to worry about that. I now have to just solve cosine of pi t equal to 0. Remember what we did from the first day of class. We replaced this with a different variable. We solve for said variable. Cosine is equal to 0 at the verticals. pi over 2, 3 pi over 2, et cetera, et cetera. We can go to the right and to the left. But then we replace y with pi t, and we solve for t by dividing everything by pi, which is the same as multiplying everything by 1 over pi, giving me 1/2, 3/2, et cetera, et cetera. Okay? You guys do the other one. Negative cosine of pi over 2x. Make sure you have the correct derivative using the chain rule. It ends up not having to matter, but it's good for making sure we are doing things correctly. Go ahead and check your answers with a neighbor. So how do you get rid of pi over 2? You'd multiply by 2 over pi. So multiply all of these by 2 and then divide it by pi. So I get y is 0 pi 2 pi. That's at the horizontals, but that's equal to pi over 2t. How do I get rid of pi over 2 to solve for t? Well, multiply by 2 over pi, reciprocals. So all of these terms are going to be multiplied by 2, then divided by pi. Well, if you divide them by pi, it's 0, 1, 2. If you multiply them by 2, you get 0, 2, 4, etc., etc. Okay? So it appears it's going to be all of the even numbers. Or 2 to the n, where n is a integer. You'll learn that stuff in college. You don't have to worry about that. What's up?
We learned K last year for like integer numbers.
So 2k when k is integer.
K. Or we didn't even like the if she told K.
K is an integer. K is an integer.
Yeah.
Okay. I usually use this z. This z is what you will find in the future is, if you take more math classes, is an integer. But don't worry about it. Let's move on to the next theorem that we need to know, the mean value theorem. We already have a theorem when functions are continuous. Who remembers the theorem that we learned that dealt with functions being continuous? IVT, what's it stand for? Very good. Intermediate value theorem says if we have 2 points on a function, and you can connect those 2 points in some way, and the function's continuous between those 2 points, we'll cover all of our y values, right? So all the y values will get hit between the 2 y values here. Mean value theorem is similar, only mean value theorem will deal with functions that are differentiable. So we will start if f of x is differentiable. Now, what does differentiable mean? Well, differentiable first implies that we are continuous. Okay, so by saying something's differentiable, you know it's continuous. It also means that there are no sharp points on the function. Okay? No sharp points. I'm going to draw the situation for the mean value theorem. I'm not going to give you the entire long definition because it doesn't make sense. I feel like the graphical explanation will help. Okay? Just like the intermediate value theorem, we're going to pick 2 points on our function. But we're not going to know what it looks like between the 2 points, but we will know that we are differentiable between the 2 points. So it really is differentiable between 2 points. We don't care about the function being differentiable everywhere. Now let's say these 2 points are A and B, and this is f of A, f of B. And I can give these points values just to help you. This is 1, 3. This is, let's say 4, and this is 5. Let's say 6. Okay, so I got 2 points. I got the point 1, 3 and point 4, 6. We know that between these 2 points, we will be continuous and will be kind of smooth in the way we're curving. Okay, I guarantee you that no matter how you connect these 2 points, as long as you are continuous and smooth curved, that there will be some value in between A and B, C, it doesn't, it can be anywhere, and there could be multiple locations, where the tangent slope at that value will equal the secant slope connecting these 2 points. Okay, now here the secant slope would be 6 minus 3 over 4 minus 1. Ends up being 1 again. Okay, so you guys try. Connect these 2 points so that your function is continuous and smooth curved, no sharp points, and then you will be able to find locations on your function where your tangent slope will equal that secant slope. I will do one, and you will not do the same one. You'll do something different. There is my function connecting 1, 3, and 4, 6. It is continuous and it is differentiable. I'm looking for a location where my tangent slope is equal to 1. Well, it appears that right around here, I have a tangent slope that'll equal that secant slope. So my C value is over here. Mean value theorem works. There you go. You guys connect your 2 points, however way, and find your one or your multiple locations where your tangent slope equals your secant slope. And the key is the C value has to be between A and B. Okay? The tangent slope somewhere between A and B must equal the secant slope between A and B. That is the mean value theorem. I'm not going to write down the entire definition. We'll just go with that. Okay, so if you connected your two graphs like this, well, you could say here. If you did something with a couple of curves, well, maybe you have two locations where your tangent slope is equal to that secant slope. Does that make sense? Should not be too difficult to understand. Now, you will be given problems where you'll be given a graph like this. And you will be asked to find the approximate locations of f that are guaranteed by the mean value theorem on the interval between -5 and 3. You guys find those locations guaranteed by the mean value theorem on that interval. Go and discuss with your neighbor. Okay, discuss. Go, discuss. Did you get it, Ms. Cha? What'd you get? Yeah, -3 and 2 is correct because we have this point -5, 0. We have this point 3, 0. That means the secant line will have a slope of 0. Well, I just need to figure out where we have a tangent slope that is equal to 0 that'll occur here and here. So when x is -3 and 2. Now, in this situation where the 2 points have the same y value, this is an extension of the mean value theorem called Rolle's theorem. Rolle's theorem is if f of a equals f of b and f of x is differentiable, then we know that our tangent slope at C will equal the secant slope, but our secant slope will just equal 0. So that's called Rolle's theorem. Do not know if you ever have to know Rolle's theorem, the name for it, because Rolle's theorem is just an extension of the mean value theorem. Okay, so as long as you know the mean value theorem, you're good. But just in case you see that word Rolle's theorem, like show that Rolle's theorem is true, well, you're just going to have to show that your secant slope is going to be 0, because maybe you have the point, 1, 5 and 3, 5. You know that however you connect these 2 points, you will have at least one location where the tangent slope will equal that secant slope of 0. Okay? Okay, good. Well, what you will be asked to do, besides maybe this is a question that will pop up possibly on quizzes or tests, is show that the mean value theorem works by actually finding the location where we have a derivative equal to the secant slope. Okay? So the question is, show that this follows the mean value theorem on the interval. What you're going to have to do is find the secant slope and then see when your tangent slope equals that secant slope. It's pretty simple. But there's one thing I forgot that we also have to do, that we have to kind of check. What was the key thing about the mean value theorem? My function must be what? Differentiable. So we want to check to see that we're differentiable. And then we will find the secant slope and then see when the tangent slope equals secant slope. Now, key is it's got to be differentiable on your interval. Okay, so if there is a discontinuity or a sharp point outside your interval, well, that's still fine as long as you're continuous and have tangent slopes inside the interval. Now, there's multiple ways to check to see that things are differentiable. So this original function, x to the fourth minus 2x squared, you know it's continuous because it doesn't have a denominator. You're actually going to check the same thing for its derivative. This will never be undefined. Since it'll never be undefined, you know that it's differentiable everywhere, right? Because it doesn't have a denominator. You can't set it equal to 0. So boom, we've checked off the first part. Next, we have to find the secant slope. All we need for a secant line is 2 points. I have the 2 points, the 2 x's. We just need to find the 2 y's for those 2 x's. So I plug in -2. I get 2, 4, 8, 16 minus 8, which is 8. I plug in 2. I get the same thing. So I have the point -2, 8, and 2, 8. And that will give me a secant slope. Ends up giving me 0. Well, I need to figure out when my tangent slope equals the secant slope. I will set f prime equal to that value. And I will solve. And actually get 3 locations, 3 C's between -2 and 2. Okay. Let's do another one. Show that the mean value theorem is applied to x squared, and then find the C values and on x squared between -2 and 1, and find the C value or C values that are guaranteed by the mean value theorem on that interval. Go. Is this you? Check your answer with a neighbor. So I get when x is negative a half. I got my tangent slope generator was 2x. It's never going to be undefined. That means my original function is differentiable everywhere. I then find my secant slope. I then set it equal to my tangent slope generator to find when my tangent slope will be equal to that value. Okay. We can do the same thing for sines, cosines, stuff like that. Let's look at this one. And then we're going to get our calculators and do some calculator stuff. Now, this is not continuous at x equals 0, right? Because if I plug in 0, that's bad. Also, the derivative, this is negative 4x to the negative first. The derivative would be 4 over x squared. The derivative is not differentiable at x equals 0 as well. However, 0 is outside the interval, so we're actually good. It will be differentiable between 1 and 4. I have my derivative. I then find the secant slope. I have the 0.43 and I have the 0.10. I again get 1. I figure out when 4 over x squared equals 1. 4 equals x squared. X will equal plus or minus 2. However, the only value that is guaranteed by the mean value theorem is the positive 2. Because positive 2 is in your interval from 1 to 4. Okay, that's the mean value theorem. Those are the types of problems you're going to do with the mean value theorem. Now, get out the calculator. Now, if you grab one of my yellow calculators, go ahead and reset it. Second plus 712. Because my stats people use calculators a lot, and they do stat plots and crazy things like that. And we don't want that going on here. See, I did a freaking box plot. So clear things out. Second plus 712, and we'll be good. All right, so let's find the critical points. I'm going to take the derivative. Set it equal to 0, see what it's undefined, and solve. Okay, ready, set, solve. Most equations in this world are not solvable by hand. Won't have nice answers. Okay, we need some computational means to help us. We need some numerical process to help us. We need a calculator to help us solve this. Now, if you have a TI-89, you could just say solve, and it'll solve for you. If you don't have a TI-89, we need to be a little bit more intuitive. We need to kind of improvise a little bit, because it's not as easy as saying solve. Here's the easiest way to solve any equation using your calculator. Okay? Any equation. It could be equal to 0. It could be equal to another number, 10. It could be equal to something with x's. It doesn't matter. To solve any equation, we will just figure out for which x values will the y values be the same? Well, I create two separate equations. I have y equals my derivative and y equals 0. If I graph y equals both sides, and then I find the intersections of those two graphs, I will have solved the equations. Let's go ahead and do that. In my calculator, I will go into y equals, and I'll type in 5x to the fourth. Let's all do this. Minus 12x cubed plus 2. And I will also graph y equals 0. It's not always 0. You can have a different number. You can have something with x's. It doesn't matter. And you will graph. And you'll see, and you won't see the y equals 0 line, but maybe if I just made sure, if you went over and made one of these kind of like bolder, sometimes that helps to see the difference. Here's my first graph, and here's my y equals 0 on top of the x-axis. I want to see when these two intersect with each other. Remember, from previous classes, you can go to second calc intersect. Second calc is over trace. After you've graphed the two equations, second calculate intersect. Now, it's important to understand we have two solutions, so we need to kind of scroll our cursor over to one of them to find my first solution, 6.606, and then dot, dot, dot for more decimals. And then my second solution, second calc, intersect up to the right over here. And my second one's 2.369, dot, dot, dot. You're allowed to truncate your answers. We typically put our answers into 3 decimal places. Truncating is fine, rounding is fine. I prefer truncating because it's just simpler. You don't have to worry about rounding up or down. Okay? So you just cut out the number right at the 3rd decimal place. Boom, we have now found our critical points. You can do this to help check your solutions while you're doing your homework. You just graph y equals the left, graph y equals the right. Sometimes you will be asked certain questions like how many critical points are there for a certain function on an interval? Well, you need to find the derivative correctly, then you need to graph that derivative and see how many times is across the x-axis really between 0 and 1. Go ahead and do that. Now, if you plug this in and you're looking for your tangent slopes equal to 0, that might take you a while. Instead, if you maybe rewrote this and took the derivative of it, understanding there's an outside, a middle, and an inside, so that you'd have 2 negative sign 6x. Maybe that is an easier way. It definitely is an easier way. Because I can just take that. I don't even have to simplify it because I know I can plug in an unsimplified function into a calculator. I'd graph it. And I see I got a whole bunch of critical points. But the question is just between 0 and 1. What is going to make this easier? No, table's not going to help me. Zoom might help me. What if I want to quickly look at a correct portion of the graph? I would go to window, and I would go from 0 to 1. It's probably best to go from like -0.1 to 1.1. That way you can see just to the right and just to the left of our guy, because it looks like we do have one at 0. And then I have one right there. I have one right there. I'll probably double check to see that I have one at 0. So second calc intersection, pop over here to 0. Enter, enter, enter. Yep. So we would have 0, and then this value and this value, we'd have 3. 3 critical points, including x equals 0. Okay? So that's the power of our calculator. Our calculator can solve any equation that we have for it, so long as we have y equals, and we can find the intersections. It can help us find how many of something we have. It might be able to help us with a mean value theorem problem where I can't solve something easily. Various different things our calculator can do. Use your calculator to help you solve for tricky ones that you want to check to make sure you have solved correctly. But the expectation is for you to do all of these by hand, and it's only a certain amount of problems on the calculator section of our AP test will you have to use your actual calculator. A lot of people will get to the calculator section of the AP test and assume that they're using their calculator on every problem, but you end up using them on like half, if not less than half the problems on the calculator section.